All right, everyone, let's take a look at our homework that we had over the weekend, worksheet number 8. First one that we need to go over here is question number 4. So let's take a peek at that one here now. It says, calculate the distance from a 3 coulomb electric charge with a field strength would be 1.09 times 10 to the 11 newtons per coulomb. We have 3 equations, right, that describe electric fields. Let's draw that little Venn diagram again, just real quickly off to the side here. We have the first one, E is equal to KQ over R squared. Then E is equal to F over Q. And then we have E is equal to delta V over delta D. Notice the vector sign over top of the E in each and every case. The second equation on your data sheet actually doesn't have the absolute value signs around it. The other ones do. Okay, if it was me, I'd put the absolute value signs around all of them. But that's the lesser of 2 things. The most important thing is that you put the vector sign over it so that you remember that it's not energy, so that you remember that it is electric field. Okay, in the end, whether you put the absolute value signs around or not, the top 2 equations go together and the bottom 2 equations go together. The top 2 equations describe a situation where we have a non-uniform electric field. In other words, okay, we're dealing with this situation right here. Okay, the electric field surrounding a positive producer or surrounding a negative producer. The bottom situation is when we have a uniform electric field. And we have a uniform electric field when we have 2 charged parallel plates, or something that's like 2 charged parallel plates, producing an electric field where the field lines are equidistant apart and parallel to each other. Now that middle equation, we can use whenever we want, right? As long as we have an experiencer, whether it's a uniform or a non-uniform field, as long as we have something feeling that field, we're allowed to use that middle equation. All right, let's look at question number 4 now. What's the distance from this charge where the field strength is this value? This is a producer, right? This is a non-uniform field, and this is a producer. We're going to use the producer equation up here. It's the very first one. Okay, there could be an experiencer there. At that distance, there could be something feeling that field. But if there is, we don't know anything about it. We only know something about this 3 coulomb charge that causes this field. So we'll use the producer equation. E is equal to KQ over R squared. We're going to rearrange it to solve for R. Okay, so let's say the R goes up, or the R squared goes up like this. The E goes down by dividing, becomes R squared is equal to KQ over electric field. And then finally, we got to square root that. We get the square root of KQ over the electric field. So we got the value of K. It's a constant, right? 8.99 times 10 to the 9. Times the charge is 3 coulombs. Nice easy value for charge there. The electric field is 1.09 times 10 to the 11. They've got newtons per coulomb, or I've got newtons per coulomb here. What other set of units could you use for the electric field besides newtons per coulomb? It goes with that last equation that we talked about towards the end of last week. Andy? Volts per meter. You could write down volts per meter here, and it would be the exact same thing. It wouldn't change anything. Okay, when we do that math there, it should work out to be 4.97 times 10 to the minus 1, or you could say 0.497 meters. Is that okay, or do we need to show you this on the calculator? Do you guys feel okay about punching that in correctly? If you need more detail for this question, or any other question for that matter, just let me know. Okay, next one we want to do is number 6. This one says, find the magnitude of the electric field experienced by an alpha particle if the net force experienced is 2.0 times 10 to the negative 16. And what's the initial acceleration? Hey, this is the first time that we've seen an alpha particle. I believe this is the very first question we've done this year where we've seen an alpha particle. I haven't even told you what an alpha particle is. How do I expect you to do this question when I haven't told you what an alpha particle is? How do I expect you to know what the charge or the mass or any other properties of alpha particles are? Kenton? Yeah. If you've got something like this and you need data for it and you don't have the data, then logically, where are you going to look? Your data sheet. When you find that on your data sheet, it's near the charge of the electron. You're going to find its charge is plus 2e. What does that mean? What does that mean? Good. It's 2 times the elementary charge, or 2 times the 1.6 value, becomes 3.2 times 10 to the minus 19. And it is positive. Now, the mass of the alpha particle, that's on our data sheet as well, 6.65 times 10 to the minus 27 kilograms. You don't need to write these down as givens necessarily, because you've got them on your data sheet. But it is a good idea to circle alpha to remind yourself that it's not an electron. Okay, what happens to a lot of people? Read this question. Do everything correct, but use the data for the electron, because it's habit, because we see that a lot. If you're that person, and this is a multiple choice question, your answer is probably going to be there, and you're going to pick it, and you're going to think you got it right. You're going to walk out of the exam thinking, oh, I did well, because you answered questions like that correct, but you didn't. All right. It experiences a force. This alpha particle, it does produce its own field, but we're not talking about the field that it produces here. We're talking about the field that it's experiencing, caused by something else. Now, something had to cause that field. We don't know what it is. We don't really care, because we have enough information about what felt the field, what experienced the field. There's the force. We're going to say E is equal to F over Q. And we're going to rearrange this to solve for, no, we're not. We're just going to solve for E there. It becomes 2 times 10 to the negative 16 divided by the charge of 3.2 times 10 to the minus 19. Again, be careful, because it's so easy to write in 1.6 times 10 to the minus 19, because that's what it usually is for us. Do that math. Do that math, and that should work out to be 625. Yeah, 625 or 6.25 times 10 to the 2. Now, we could have also used volts per meter, but it probably makes sense to use newtons per coulomb here because of the equation that we used. Now, we want to find the acceleration. I've told you guys, every time you want to find the acceleration, physics 30, do this. What is it? Mason, what are you going to do there? Every time you want to find acceleration, what should you try? Every time. Every time. Nobody? Terry, you got it? Yeah. Let's go. F is equal to m times a, right? Newton's second law. Now, when I say every time, try this, I don't mean every time it works. I mean it works pretty much every time. If you try F is equal to m times a and it doesn't work, it's that 1% chance that it doesn't work, well, then try something else. But if it works 99% of the time, that should be the first thing that we try, right? It should be our go-to step. Tara said A is equal to F over M. We already have F. We were given in the question, 2 times 10 to the minus 16. We already have M. We just figured it out a minute ago from our data sheet, 6.65 times 10 to the minus 27. And when we do the math on that one, we end up getting 3.01 times 10 to the 10 meters per second squared. Now, I'm just going to make a comment about that number. Some of you may know this, some of you may not know this, and it's okay either way, because I haven't taught this yet. Okay, that comes later on, 2 units from now. The speed of light is 3 times 10 to the 8 meters per second. That works out to be about 1 billion kilometers per hour. That is the maximum possible speed that anything can travel. Don't worry, it's fast. Okay, it's fast enough where, let's say you were to turn on a flashlight in Halifax, and it could actually go across the country to Victoria, and then back again and back again and back again. It would make about 30 return trips across Canada in 1 second. That's how fast light travels. It's really, really, really fast. But there is an upper limit to it. Okay, there is an upper limit to it, 3 times 10 to the 8 meters per second. It can't go faster than that. Nothing can go faster than that. So, when I see this number, 3.01 times 10 to the 10 meters per second squared, that's bigger than 3 times 10 to the 8. Does that mean that I've made a mistake here? Parker? Thought I saw your head kind of shaking there. No, I haven't made a mistake. That's right. So how do we explain that? If the maximum speed is 3 times 10 to the 8 meters per second, and we've got 3.01 times 10 to the 10 meters per second squared, how do we explain that? Yep. Yeah. Good. There's no upper limit to acceleration. It can be 10 to the 50 meters per second squared. All this means is that it would get to its maximum speed of less than 3 times 10 to the 8 really, 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 really quickly. That's all. Okay. I've seen accelerations of 10 to the 50, 10 to the 60 meters per second. And that's crazy fast, crazy quick acceleration. But it says nothing about speed. Okay, maybe the maximum speed is 28 meters per second. It just gets there really, really quickly, that's all. All right, next question that we needed to go over was number 8. Now we start getting a little bit trickier here. 8 says 2 charges are in a straight row. The first charge has a value of 5 times 10 to the negative 5 coulombs. The second charge has a value of negative 2.5 times 10 to the negative 5 coulombs. And they're 4.5 centimeters apart. So that makes that point in the middle where we're trying to find the field strength right here, midway between, okay, it makes this distance 0.0225 meters, right? 2.25 centimeters. And this one is also going to be 0.0225. All right. Some of you, I know you do this because I walk around as you're working on things and I see you doing this. Or I should say not doing this. Everybody should be doing this though. Draw the pictures I have right here, but also draw the directions, Mason. Also draw the direction of the field. Which way does the field go caused by number 1? Well, it's positive. If charge number 1 is positive, the field will go away from it because electric fields go away from positive producers. What about charge 2? It's negative. Field goes toward negative producers. So field 2 is also going to point to the right. Now in this question, because they're both to the right, if you didn't draw the diagram and you didn't recognize which direction the fields were in, you probably would have still gotten this right because you would have added them together. Okay, but it's a 50-50 chance at this point if you don't draw the diagram. Okay, and I don't know about you, but that's not good enough for me. I don't want 50-50 chance. I want a 90% chance I'm going to get a question right, not 50. All right, let's calculate E1 and E2. It's KQ1 over R squared. Q1 is 5 times 10 to the minus 5, and the distance R is 0.0225, and we got to square that. We do that math. The first field there for number 8 works out to be 8.879 times 10 to the 8. We can say newtons per coulomb, we can say volts per meter, doesn't matter. E2, we go about it in the same way, just drop the sign of the charge there. Gives me 4.44 times 10 to the 8 newtons per coulomb. Now, what are we going to do with these? Add them up. We're going to add them up positive, negative, both positive because they're both to the right. But be careful. If one was drawn to the left, we'd add it up as a negative value. So when we do add those up, we end up getting 1.33 times 10 to the 9. Say newtons per coulomb, or we could say volts per meter. Number 9, real similar question actually, but there's a couple of things in here that can mess us up. Not conceptually difficult things, but just little things that can mess us up. Firstly, we got 3 charges instead of 2. They're in a row. Here's 1, here's 2, here's 3. First one is 2.5 times 10 to the minus 2. Second one is negative 4 times 10 to the minus 2. And the third one is 3 times 10 to the minus 2 coulombs. Well, I don't like this. See this 60 millimeters, 5 centimeters, 2 centimeters? Let's do that conversion now, because not only is there a conversion involved in this question, but it's two different conversions. 60 millimeters is 0.06 meters, 0.05 meters, and we're trying to find the field strength out here, 0.02 meters away from charge number 3. Draw the picture. Draw the picture. Okay, which way does the field point at point X caused by number 1? To the right. It's away from the positive producer, number 1. James, which way does the field point at point X caused by number 2? Good. It points toward the negative producer. Mason, which way does the field caused by number 3 point at point X? Let's help them out. Shaylin, you got that one? Which way does the field point caused by number 3? It would point to the right. It would point away from a positive producer, right? So now we got 3 of them, which is one more than we had in the last question, but that's okay. This means that we have to calculate 3 of them, right? When we do calculate them, E1 is going to work out to be 1.3299 times 10 to the 10. E2 is going to be 7.3388 times 10 to the 10. And E3 is going to be 6.7425 times 10 to the 11 newtons per coulomb. Hey, what distance? Quick question for you. When I'm calculating E1, what's the value of R that I would use? 0.13. Yeah, why? Josh, 0.13 meters. Good, excellent. We don't want this distance right here, or this distance, or this distance. We want the distance from here to here when finding field number 1, and that's going to be as a result of adding those 3 numbers together. Okay, let's add these numbers together now. When we do that, make sure that this one is a negative value. And when we do, we should get 6.14 times 10 to the 11 newtons per coulomb, and it's to the right because it's a positive value. Okay? Finally, last question we need to go over here, number 12. An electron sits between 2 charged parallel plates 10 centimeters apart. The field strength between the plates is 2,500 newtons per coulomb. The electron sits between these 2 plates. We got 3 equations, remember. E is equal to KQ over R squared, F over Q, and delta V over delta D. So we circle, right? Top ones are non-uniform, bottom 2 are uniform fields. Which 2 equations am I allowed to use here? Red or green? Green. We've got parallel plates, right? So we're allowed to use the 2 bottom equations. This is the distance between the plates. Probably a good idea to circle that centimeters. This is the field between the plates. We want to find the potential difference. Look, we're allowed to use the bottom 2 equations. The one that fits there, probably E is equal to delta V over delta D. And when we do that, we get 2.50 times 10 to the 2, or 250 volts. Again, hey, these top 2 equations, or the top equation, I should say, out the window. This is what we're allowed to use. Bottom 2 are what we're allowed to use here. Want to find the magnitude of the force. Well, we've tried one of them. Let's try another one now. E is equal to F over Q. Q is the electron, so it's 1.6 times 10 to the minus 19 times 250. That gives us 4.00 times 10 to the negative 16. And finally, Mason, I'm going to ask you this question again because I asked it earlier. I know you know the answer this time. When you want to find acceleration in physics 30, what are you going to do? Good. You're going to use A is equal to F over M. That's at least what we're always going to try. 99% of the time, I'm making that number up, by the way, but pretty much all the time, it's going to work for you. If it doesn't work for you, well, then we can try something else. But since it works pretty much all the time, we might as well try that one first. Okay, try the one that works most of the time first. A is equal to F over M. We got the force here. It's 4 times 10 to the negative 16 divided by the mass. The mass of the electron is 9.11 times 10 to the minus 31. When we do that math, works out to be 4.39 times 10 to the 14. Is that number okay? 10 to the 14 meters per second squared? Sure. It just means that it's going to accelerate to its maximum speed. It's going to go all the way across these plates and get going at its maximum speed really, really, really quick, virtually instantly, right? Okay with those questions?